All right. So number of complete cycles per second of a wave, that's frequency, and then amplitude, of course, maximum displacement or disturbance caused by a wave. All right. So um all right. So remember that the two main waves we're going to look at throughout this topic is sound and light waves. Those are the two main waves. Um so now so what we should look at before we even touch that is the parts of a wave. And this is labeling. All right, so labeling a wave. All right, so let's see if we can bring up some of the parts of the wave that we would need to label. That's potentially a question that could come. If them send it along the easy path, but let's see what happens if they do that. All right, so looking at the parts of a wave, and we're in focus on the transverse wave when we're labeling. Do we have the other waves? Definitely have the same things, but transverse waves that are more easier to identify. All right, so guys, this is what we mean when we say you should be able to label a wave. So looking at this diagram, you're seeing various names used to describe parts of the wave, and we're seeing, let's just start to identify them by number. That's one, that's called a crest here. 2 is a trough, and let's label 3. This would be the amplitude. All right. Again, we already defined amplitude, but now we know where on a wave it would be found. And now we are introduced to this term now called wavelength. So wavelength is another important and interesting concept when it comes to waves. So this would be our fourth thing to label. All right. So looking at the diagram now, and even before that, this dotted line that goes through the wave, that's actually rest. That's a rest position. All right. It's where the wave would be if it wasn't a wave. Or in other words, if there was no disturbance, then that's where it would be. All right. No. Any questions so far, guys? So we're looking at the not still. All right. So basically, we're going to look at them individually. So the crest, based on what you're seeing there, how would you describe? How would you describe it on the diagram? What part is it pointing to?
So above rest position.
Above rest position. uh, no, I wouldn't. No, that's not how I would describe it. Above rest position. All right. No, more than that, and it's actually more simpler than that.
So we can try again.
No, somebody else. Make somebody else go on.
Sir, please can you repeat the question?
So you never heard the question?
No, sir. Sir, my Wi-Fi was in and out.
All right, where's the Chris pointing to? Where is it pointing at? It's there the whole night. It's the things I got to tell you now. And I must use common sense.
Sir, the beginning of the wave.
The beginning. All right. So let's identify the beginning of the wave. So the wave would start here. This is the rest position of the wave. So that is the beginning. So you cannot say that.
It's the highest point going upwards from the rest position.
Highest point from the rest position. That sound like a different one. That sound like the amplitude. So if
Where like the disturbance is like high.
how about saying that it's the top of a wave? You know the word top of a wave. That's what the crest is. All right. So some of you guys go to school and don't know where on crest. Where the crest? You know where at the top. Considering your uniform, it's at the top. No so. Crest come in like crown. Crown we're at top. So the crest is the top of something. So I don't know why you guys overthinking the thing. Alright, crest is the top of a wave. That's it. So the arrow is pointing at the top of the wave. Alright. You already know what amplitude is. So and notice that the arrow for amplitude points the other direction. It points from the rest position to the crest. Now that's different from actually literally pointing at the top of the wave. So the top of the wave is called the crest. So what would the trough be?
Bottom of the wave.
Yeah, that's it. All right. So the crest is the top of the wave, trough is the bottom of the wave, amplitude is the maximum disturbance. So the maximum displacement from the rest position. That's what you'd have for your definition here. And of course, we're going to look at wavelength. Now, how would you define wavelength based on what is in the diagram?
The distance between a crest and another crest.
Okay, yeah, I like that. Yeah, if they ask you that in exam, you get marks there. You certainly will get marks. That's well done. That's Giovanni. All right. So I think okay, Janari has some issues here. Let me just allow him. Yeah. So again, wavelength. The distance between two same points of a wave, or as you say, distance between two crests or two trough. That's acceptable. Okay. So The wavelength is a distance. Now, let me just. Two same points on a wave. All right, so that's the wavelength. All right, so up to this point, you should be able to define or state what four parts of the wave would be, and identify where they are in the diagram. All right, now the other terms that are missing. Some diagrams have more, and I think in terms of definition, these are the main parts. All right. You guys have any question? Okay, now other concept now, guys. Other thing that I should point out to you guys. This little letter here. So it's a Greek letter. And
Lambda.
what's this letter?
Lambda.
Yeah. Lambda. All right. So yeah, that's the symbol for wavelength. All right. So yeah, and so that covers labeling the wave for the most part. I'm trying to see if we forget anything. No, I don't think. All right. So with that said, moving on then. All right. Maybe I should point out to you that wavelength is measured in meters. Well, amplitude also measured in meters too, but you know, we don't usually measure the amplitude of a wave because most of the wave is not seen. But the wavelength of a wave can be seen. So believe it or not, it can be seen and it can also be heard. That's the beauty of wavelength. So the wavelength that is measured in meters. However, you know, in let me just write the lambda properly. All right. However, in science, well, in scientific applications, we will say that the wavelength is measured in another unit. In scientific applications or in industry, wavelength is often measured in, and the units are here, nanometers, and that is written as common N, common M. All right, so which is 10 to the minus 9 meters. So that's basically what it is. All right, so that class is wavelength, the importance of wavelength. All right, now also the wavelength, and we say that the wavelength of a wave can be seen. Well, the wavelength of light is actually seen color. It's actually a color, and it's very visible. Wavelength of light visible. All right. Whereas now we could say the wavelength of sound that can be heard. the wavelength of sound. All right, this is interesting now. All right, and now let's see what we hear around us that tells you about wavelength. What to put it this way now? The frequency and the wavelength are actually inversely related. And so what basically happens with sound is that the higher the frequency of the sound is the smaller the wavelength. And that's how it works. So what happened here is that the wavelength of sound, which can be heard, all right, and this is your color. I should point out this to you. Wavelength of waves. So for example, I should put it in a real life situation. I know the problem is that we normally use frequency to instead of wavelength of the sound. But all right, but let's put it even simpler than that. If somebody talks, if somebody sings high, let's say it's you probably know some singing voice already. All right, so it's like you can hear anybody know what I mean by soprano? All right, so soprano has actually have a high wavelength. Sorry, that's a small wavelength. And then bass have a very large wavelength. All right, so let me show you a thing now. When if somebody is talking to you, like up front, all right, somebody is talking to you up front, you can hear them more clearly, right? Like they're right in front of you than if they were to be moving away from you. All right, now ever experience somebody talking to you and then moving away? You notice any change in the sound as they move away while them still talking? No. All right. This way in a car and then you pass another car. Is there a change in the sound as the car come to you and the car
Yes, sir.
pass?
Yes, sir.
All right. Yeah. So that's a better way to look at it. All right. What the difference here?
Sir, it's like you start fade.
Start fade. All right. The car sound different when it coming towards you.
Yes, sir.
All right. Is it does it sound more bassy or it sound lighter?
Sir, it's on BSC, sir.
All right. So when it's coming to you, it have a bassier sound, and when it's leaving, what type of sound it have?
Soprano, sir.
Hey, we're using the word soprano. All right. Soprano is actually a singing voice though, but all right.
All right, sir. It kind of sound soft now.
Yeah.
It has fade, sir. All right,
Yeah,
sir.
yeah.
Just like the bike, sir. They call the Zoom Shing bike, sir. Perfect example. Even though them always loud, but you hear the difference, sir. From when you're further from you than here.
Yeah. There you go. All right, and and there's a reason for that. Let me just show you something then. All right. So like about a century ago, a guy by the name of Johan Doppler, all right, sing January, saying that it gets louder. All right. No, a guy named Doppler. I think he's a European. I think he got a Nobel Prize for it too. But this guy actually discovered that an effect where when when an object that's making a sound moves past a person who is listening, there's a change in the wavelength of the sound. All right, the change in the wavelength is what's used to describe the sound. So let's see if we can bring up that effect here. It's actually called a Doppler effect. And all right, let's see. All right, and I'm gonna show you a little image here in a sec. All right, now as soon as it loads, all right, here it goes. All right, I'm gonna share this with you guys. Everybody seeing the screen?
Yes, sir.
All right. So let's want you to observe something here. Hopefully they oh shoot, never share the sound here. All right. It's there now.
Good evening.
Leaving John Antonio. All right. So here goes.
In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
All right. Stick up in there. Did you hear what you just said a while ago?
No, sir.
Wave caused by relative motion between the source of the wave and the observer.
All right. Anyway. And
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves.
All right, so stick up in there. All right, so we see that they give 3 examples there, right? Fire engine, and duck in water. All right, all those. All right, and notice that the waves are shown as circles leaving the object. All right, so pay attention to that. All right, let's go.
Waves moves. In the direction it's moving, the wavefronts bunch up.
All right, watch this now. All right, everybody seeing the screen?
Yes, sir.
Yes.
Yes, sir.
All right, so we're seeing that when the wave is moving, do you notice a change in the size of the wave when it moves? Let's go back to where it started. So it looked like this before, right? And then now, and then watch it now. You see it changing now? You see the distance between these circles are changing. All right. So again, pay attention to that.
The wavefronts bunch up, and behind it, they spread out.
All right, watch this now. So you see, when it passes now, you notice it get bigger. You see it?
Yes, sir.
All right. All right, good. So let's continue watching.
If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency.
All right, so stick up in there. Again, the point I'm trying to get to you guys is that higher frequency means shorter wavelength. All right. You know that the wavelength here is short because they bunch up closer together. And so that's a short wavelength. The distance between the waves are shorter, and then we see that as high frequency. All right, so let's continue.
And if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
All right, there you see lower frequency. Now, again, that's the lower frequency is the bassier sound. So again, that's what we use. And so if, for example, somebody is keeping a party or a stage show, and you will realize that from as far as you can make it out, you will hear the bass before you hear anything else. All right, you notice that with it, you live or you stay some distance from a party down the road, you hear the bass. first. You hear the bass like it louder than everything else. But observe that.
Yes, sir.
Yeah. All right. Welcome to your class tonight. Oh, everybody's so quiet. What time now? The man no. All right. Anyway.
So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
All right. So yeah, changing the frequency of the wave. Remember, guys, if frequency change, wavelength change. All right. So the idea with frequency again is anything will happen to the frequency, the opposite happen to the wavelength. They are inversely related. Yes. All right. So
It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this.
all right. So you notice that sound? That change in the sound as the car passes? See, real life thing.
Something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective,
Yeah, see, it start at a high pitch, end up on a lower pitch. All right, so
and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on?
all right, so remember now the horn have one tone, but yet when it pass, so when it coming closer to the person, it have a different sound than when it is leaving the person. All right, so
As
better.
the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star.
It's going down. All right. So again, that's a sound. So let's observe.
Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right.
Over 50,000.
All right, guys. So all right, guys. So did you learn anything from the video?
Yes, sir.
So that's Benito. What happened to everybody else?
Yes, sir.
Yes, sir.
All right.
Yes, sir.
All right. So let's go back to the sharing. All right. So and okay, the screen one. Let me just get the video panel up. All right, so guys, that's the principle here. So the wavelength affects the color of light, and it affects the tone of the sound, or they call it pitch. You can call that. All right. And so we're also going to add to that is the relationship between those things. All right. So frequency maybe calculated. And the frequency may be calculated in various situations, right? All right. Example. All right. Example 1. Using the periodic time of a wave, right? So periodic time. All right, so the periodic time of a wave. All right, now I should point out this here. They could ask you to define the periodic time. So it's something that we would need to know first. So periodic time, the periodic time of a wave, all right, is the time a wave takes to complete one complete cycle. All right, so the time right, time taken by a wave to complete a cycle. All right. All right. So now, so therefore, we use this formula then. In seconds, by the way. Let me just scan it in seconds. All right. The periodic time is measured in seconds. Yeah, so it's measured in seconds. All right. So now, so we use this formula, the first wave formula, which would be, it's very simple. That's 1 over time. And remember, this time is actually the period time, the periodic time. And then this gives us the frequency here. All right. Now, another thing to point out to you guys is that frequency is measured in hertz, right? And hertz is written as
Yes, sir.
Hz. Yeah. So just point out that frequency is measured in hertz. Now, time in seconds, frequency is measured in Hz. Frequency is measured in hertz.
Sir, can you hear me now, sir?
Yes. All right. Frequency is measured in hertz. Now, so note frequency is measured in hertz. Again, a lot of these units, if they sound strange, it's because they are named after a person. So the hertz was named after I think it was Gustav Hertz. Believe it was, this German guy.
Sir.
Yes. Who is that?
Sir,
Chanel?
one that over top there, sir?
Yeah, it's 1.
Yes, sir.
It's
and
a
time,
yeah.
time there to the right.
Yeah, time is it? Yeah, to the
Sir,
right.
what they be under the time?
The seconds, the unit where it measuring. Let me just zoom.
Okay. Sir, my phone, may I see it blurry? On my phone.
Okay. All right. Well, to find a way to optimize this thing for the phone though. Probably need to. Still not get no phone yet, but sort that out. All right, I'm trying to get it at the right size about that. All right. So remember, guys. All right. So far, please remember that frequency is measured in hertz. But then the hertz hertz is actually equal to second to the -1. So definitely something to remember still. All right. So so can I move on from here? Our persons are still writing.
Still writing, sir.
Okay. All right. So again, we have two ways to calculate frequency at CXC level. And one method is to use the periodic time of a wave. And this is, you know, in reality, this is not, you know, it's don't really apply. To me, it don't apply in real life. I don't say where in real life you would want to know the periodic time of wave. You more want to know the frequency, you know. And so for a real life application, it's frequency we use. But then in case CXC asks you a question about periodic time, then you know this is the formula you use. So when you get the frequency of a wave, basically you just invert it or put 1 over it and you get the periodic time. So that's why we use this triangle here. This triangle is saying that 1 over time is frequency and 1 over frequency is time. All right. So in a question, they'll give you one or the other, but the one is always up top. So it all depends on which one them give you. All right. And see if we can bring up a question to highlight that fact. Okay. So not seeing any here, but all right. All right. So well, them not have it in the triangular form. They have different formulas here. All right. Let me give you all right. All right. Well, this.
So I think you can move.
Oh, then?
You can move on now, sir.
Yeah, move on. Okay. All right. All right. Let's see. All right. I'll give you trying to find a question that can fit this. All of them seem to be above your level. So I have to go improvise. All right. Yeah, no problem. All right. Let's move on then. All right. All right. So basically, so a wave So a wave has a frequency of 50 hertz. Calculate the periodic time of the wave. All right. So let's see a question like that. 50 hertz. And 50 hertz is about the frequency of the current, you know, of GPS current. So a wave has a frequency of 50 hertz. All right. Calculate the periodic time of the wave. All right. So in reality, 50 hertz is a sound that you probably can you hear 50 hertz though? Well, you can hear from 20 hertz all the way up to 20,000 hertz. 50 hertz going sound like you probably will feel it more than you can hear it. I mean, if you hear them really good, you will hear it. But 50 hertz is a bass. As a matter of fact, yeah. Let me see.
So probably about 20.
Yeah, you can hear from 20 to 20,000 hertz. So that's the range you can hear if your ears them working at full potential. All right. So 50 hertz now. This is why when things are plugged in, what kind of sound you hear when things plug in and work? Like beside the fridge or anything we draw current. You hear does it make a sound?
Yes, sir.
Yeah, what type of sound you hear?
Like a ball.
Like a
Like a ball.
buzz?
Yes, sir.
Okay. All right. It sound like yeah. All right, we could say a hum as well. So
Yes, sir.
yeah, man. So as we say, with this type of sound now 50 hertz is a hum, a little rumble like. All right, so that's why when motor plug in and it vibrate, you have 50 hertz. About that's the sound that you're going to come across as. But then in this question now, them ask you to find the periodic time of the wave.
So you say 20, sir, I think.
20. All right. The period time of a wave is you will call this let's call this periodic time. Okay. And then that's right here. That's what you're going to calculate. The formula say 1 over the frequency. And then you're going to end up with 50 being the frequency. All right. So periodic time is equal to 1 over 50. All right. 1 over 50. And then now, what's that number? You should get 0.
0.02.
0. What?
0.02.
All right, very good. 0.02 seconds. All right, and that's it. That's it. So
Oh,
see,
yes, sir.
yeah.
Yes, sir. So we have in a millisecond or something extra, so. MS.
Oh, well, okay. Well, or if you have it in milliseconds, which again CXC could use that trick on you as well. So yeah, let's just learn how to work with milliseconds. All right. So it would be the same thing as what? 20 milliseconds. It's actually 20 milliseconds if you go this way, or 200. It's actually going to be 20. All right, 20 milliseconds. So
Yes, sir. Richard.
yeah. So, and again, this is 20 milliseconds. All right. Yeah. So that's one way you could get a question. And Kayla, writing this off?
Excuse me, sir.
Yes, dear Chanel.
Sir, I want 20 ms that.
Yeah.
Sir, is that in the solution?
No, we don't need a solution, dear Chanel. But we know say 0.2 seconds is the same thing as 20 millisecond. As 20 millisecond,
Oh, I see.
yeah. You know,
Okay, sir.
yeah. And again, as I said, this millisecond thing come up. We are gonna look for our next question now. We put the time in millisecond and ask if we find the frequency. So let me know when I can move on.
Yes.
You can.
All right, good. So let's look at another type of question now. So all right. So wave has a all right. So a wave has a periodic time. Let's call it yeah. So that would be like 350 milliseconds, right? So calculate the frequency of the wave. All right. So
Sir,
yes.
2.9 hertz.
Yeah, 2.9 hertz you have there. Let's see now. 2.9. All right. So let's look at that. State whether the frequency of the wave would be audible, visible, or tangible. So you see, this is the real life thing. This is a real life thing, you know, guys. Where wave, when you talk about wave, you're supposed to can either see it, all right, feel it, or hear it. All right, one out of three or all of them, you know, depending on what's happening. So that's the beauty of wave. So it's either you see it, hear it, or feel it. So now, when you work out, when you get the answer for A, then you're supposed to can use your knowledge now and say, well, can I hear this wave? Can I see it, or can I feel it? You know which frequency you can see already. So yeah, so you know which frequency you can see. So you see.
Sir, probably can't hear it.
Well, you can hear it. Well, that assuming say you get the right answer, January. Assuming say you get the right answer.
Sir, my second Wednesday.
Your second Wednesday too. All right, dear Chanel. All right, let me see what I go on. All right, dear Chanel somehow get the same answer where January get. All right, good see now. One up here, so. All right, and then now what we have here now. We have the frequency then give you. Now they ask for your frequency. All right, this is unknown. All right, so that's unknown. So it's 1/350. All right, there's a 350 millisecond.
Sir,
Yes.
what does tangible mean, sir? What do you mean knowledge, sir?
Hmm?
What do you mean knowledge here, sir?
I think I spell it, you know. Sorry, I spell it wrong. Can't even remember. Say not even tangible spell with I. All right. What tangible means you can touch it, you can feel it. So I mean some waves you can feel them. Like if you're under like earthquake, don't you can feel earthquake?
Yes, sir.
Yeah, that's tangible. That's a tangible wave. So once you can feel it, it's tangible. So usually a wave is tangible when it don't reach the frequency where you can hear it. It's below the frequency of hearing it. It's actually tangible before that. So again, when them say people must have sense, it not really means say a school you forgot. It means say you must be observant of your surroundings. Alright. So you'll be sitting at your home good and you can feel when something happen. Alright. Dogs know the same thing. Dog them know what go on from far because for them hearing no different now. Them can hear up to 40,000 hertz. Them can even hear some low. They must probably can all hear about 2 hertz on them the frequency there. So again, that's why dogs are good to have. Dog pick up that. Alright. Dog even know when you're dead too. If you're sick and you're dead, the dog know. They can hear things in your body. So anyway, point is that understand what you're working with here. 350 milliseconds. This we have to go do something to it. Well, you can work with it directly, but then that's another story. But you just learn it now. 350 seconds. Alright. Milli means what? This milli. What prefix milli mean again? Milli mean what? They are divided by 1,000. So that I'll give you 35 over 100 now. 0.35 seconds that. So you have to convert the milliseconds to seconds by dividing milliseconds by 1,000. Because 1,000 milliseconds make 1 second. And so 350 divided by 1,000 is going to be 0.35. So the number you're going to put in here at the periodic time, which should be in SI units, is going to be 0.35 seconds. And you're going to have 1 over 0.35. And that's how you're going to get this answer here. So this is probably value 3 marks here. You're going to change the seconds, milliseconds to seconds, then put in the seconds in the formula. 1 over 0.35. What is the answer there?
2.85.
2.9.
2.9. So that's the answer you got there, Chanel and Janari?
Yes, sir.
All
Yes,
right.
sir.
2.9 hertz. All right. Boom. So, Janari was saying you probably can't hear this.
Sir, no,
I mean, if you could hear it, I mean,
Sir.
you'd be a great person. I mean, you'd be like an X-Men. Yes, dear Chanel. Oh. All right.
Sir, me never change out it was, sir. Me never
You know,
change the millisecond to second.
if you need to change it out and get 2.9, that means to say then you do something wrong. Yeah. All right,
Sir,
2.9 hertz.
Later, yes, I get the same thing.
You cannot get the same thing there, Chanel. You're forgetting numbers or you're not reading the calculator properly. It's gonna give it to you in standard form. All right, so it's gonna
Sir,
give it
probably in a standard form. Come with this CD look times x to the
exactly.
negative
Exactly. So
with a wonder.
exactly. So if that was CXC, you would have to write out everything that you get. You couldn't just write the 2.9 and left it so because it not gonna work all the time. So all right, okay, so it's 2.9 hertz, and the question say would it be audible, visible? All right, so would it be audible? What is our range of hearing?
consider a range of hearing.
Yeah.
sir, so we couldn't hear it then
No,
because we can hear up to 20 hertz, okay?
from 20 go all the way up to 1,000 to 20,000. Sorry.
Oh, so we hear it then.
Yeah. So no, but this is 2.9.
Sir,
So how you feel hear it? The lowest you
so I
can
think
hear
you
20.
can 20.
The
Oh,
lowest you can hear 20.
sir, we can't hear you.
Okay.
You can't hear it. All right. I'll leave you with that chart here. All right. This little chart here can give you an idea of what's happening here. So see what's happening here. Humans, you see they have humans here, so 20 to 20,000. We can hear that. All right, but then you have other animals now we can do better than that. So like for example, elephant now. All right, elephant can go from 0 all the way to 160,000. Look at that. Look at that range. Dogs in the green range here then can go just above. Well, so we can actually hear lower sound better than dog though. But well, it's interesting. I think yeah, that's a lot
So I
debate.
don't think you are able to see or touch or hear it, sir. Nothing you are able to see, touch or hear, sir.
You can't see it. You can't see 2.9. Definitely, you cannot see it. So let's cross over that. So it is not
I don't
audible
think.
and it's not visible. So most likely,
Sir, it's tangible.
yeah,
It's tangible.
yeah, it's going to be tangible. All right,
You can't try to touch it, sir. You can't try to touch it.
you can feel it with your hand or with your skin.
Yes, sir. Like, you feel the vibration.
Right. So, and that's it. All right. So, all right. That's the first part of calculating frequency, and then so we're out of time now. So some of you some of you know, have class and gone. So, all right, guys. So this is it. So we're gonna stop here for today. But
Yes, sir.
you have any questions about this topic? You think you're understanding it?
Yes, sir.
Yes, sir.
All right,
Yes,
good.
sir.
Yes, sir. I'm understanding it.
Yes, sir.
All right, good. So we will continue this then. There's another formula for frequency. And so we're going to look at that next class and look at some other examples. All right. So until then, enjoy the rest of your evening.
Yes, sir. Same to you, sir.
All right.
Same to you,
Good.
sir.
All right. Thanks. And then let's close this.
All right, it is.
Yeah, man. All right.